video one's problem is about a rock that was originally all uranium, and then over time it has undergone decay, and there's now some lead in it as well, and we're asked to find the age of the rock. And this one was broken up into steps that you can pretty much just follow. So we're given this information that will also help us, so I just wrote that up there. Part A is how much did the lead weigh as uranium? So we know that the rock was originally all uranium, and now some of the uranium has decayed and created lead, so there's some lead in the rock as well. So we can convert the lead back into uranium to see how much it would weigh as uranium. So we have 1.63 milligrams of lead-206, and then 206 milligrams of lead-206 is in 1 mole of lead-206, and then 1 mole of uranium-238 is 238 milligrams of uranium-238. So we have that the lead-206 weighed 1.88320383 milligrams as uranium-238, and that's going to help us figure out the total mass of the rock as it was originally all uranium. I didn't, for talking about sig figs, I kept all of my digits, all my decimal places from my calculator, and then figured out significant figures at the end, because the question that we're asked is determine the age of the rock. And so these are intermediate steps, and this is the final answer. So my final answer has the correct sig figs. But if you are really worried about significant figures throughout the process, then we're limited by 3 for this step, 3 for this step. But yeah, that's how I did the significant figures. Okay, so now part B, we're calculating the total mass of the rock originally. So now we have the lead as uranium, and then we add that to the uranium that's in the rock in the present day, which is 5.51 milligrams. So we have 5.51 milligrams of uranium-238 plus the 1.88 milligrams of uranium-238 that was converted into lead, but we converted back to uranium. So we have that the rock originally weighed 7.39320383 milligrams of uranium. Now part C, we're finding the rate constant of the nuclear decay so that we can plug that rate constant into this equation that relates all the things that we have to the time, the age. So we find the rate constant by doing the natural log of 2 over the half-life, which you can pull from not the index, the back of the textbook. So we have 0.693 divided by 4.47 times 10 to the 9th years, which is billion years, that's the half-life. And then you get that the rate constant, the lambda, is 1.550335557 times 10 to the 10th over years. So then to find D, this is the question that we've been trying to answer from the beginning, is how old is the rock? So we have the equation from the textbook that relates the time to all of the information that we have. So we just plug in what we have. So we have 1 over the rate constant, which we just calculated, and then times the natural log of the amount of uranium in the rock now over the amount of uranium in the rock originally. And that gives you this very long number, 1.896341454 times 10 to the 9th years. But with significant figures, we're limited by 3. And so the answer is that the rock is about 190 billion years old.